Hello everyone, welcome back to Electronics 1. To wrap up our discussion on diodes, I want to come back and revisit our large and small signal operation and just look at how we would solve for the combination of that large and small signal, and or the operation with both a large and small signal applied. And this is going to become very relevant as we move forward to talk about transistors, because we'll often have a large signal or a bias circuit that we have to solve for, and once we know those bias conditions, then we can solve for the small signal operation. So okay, but again, we'll start with a diode that has both a large signal and small signal component applied. Okay, and we'll come back to talk about what defines large and small signal here in a second. But if I were to draw a diagram for this, let's assume that my large signal is some DC bias applied to my diode. I'm going to not even show a current limiting resistor. I'm going to assume that that large signal component is just the voltage across the diode. Okay, so this large signal, let's call this, try to be careful about our nomenclature here, uppercase V, uppercase subscript, to represent the large signal or DC component, and for the small signal AC component we'll put a lowercase v and lowercase d. Okay, so this will be the small signal component that's applied to our diode. So the total applied signal is simply the sum of the two. Okay, and we'll call that lowercase v for our combined or total signal with an uppercase D. Okay, so it has both the AC and DC components included. Okay, and again here, this being my large signal or my DC value, this being my AC quantity. Okay, and we spent a lot of time talking about the relationship between our diode current and our diode voltage, and we know that at least the simplified form of the equation says that our diode current is approximately equal to our saturation current times our the e to the diode voltage over NVT. Okay, and I'm showing my total signal here in my exponent, right? And if I break that out, I can say that my total diode current is equal to e to the VD, my DC value, plus my AC quantity, all divided by NVT. And if I take this just one step further, I can take the exponential and break it up into the DC component or the bias component times the AC component or the small signal component. Okay, so let's look at this on a IV curve. So if I take and draw my diode characteristic, as we all know, my relationship between my diode current and my voltage is exponential, as depicted in my equation. Let me try to. Okay, and my DC or my large signal component is going to determine where precisely I'm operating from a large signal perspective. Okay, so this would be my operating point as defined by my DC component, or as I said, often referred to as my bias. Okay, so that's due to this component of the schematic that I'm showing here. Okay, and at that point I'll have some DC or large signal current associated with that large signal or DC bias. Okay, if I now consider the AC component, so I'm just going to extend this voltage axis down here a little bit, or that voltage operating point, and my let me do it like this. Let me leave this in green to represent that's my operating point due to my DC bias. But on top of that, just turn myself sideways here, I have some small signal component operating on top of that. Okay, and that small signal component, of course, is going to cause some fluctuations in the operating around my operating point, and of course it's going to cause some variation in my current through my diode, right? And here's a slightly prettier version of that diagram that's taken from Cedra Smith's figure 4.15. Okay, so same idea. We show the operating point due to the DC bias. It's labeled Q on this diagram, and then we see the fluctuations in the applied AC voltage, or the small signal, is causing those fluctuations in the current around that operating point. And we'll come back and talk about the small signal resistance associated with the AC component, or the small signal model at that point, as we look at the slope at that point. But let's come back to that. Okay, so I said that that my diode current is going to be a function of my large signal, or my bias, times the small signal component, right? And this part, this is again just our diode current from the DC component. So I could write this just as my diode current due to the DC component times the component due to the small signal. Okay, if we take this and do a Taylor series expansion, we can show that exponential term, e to the x, is equal to 1 plus x squared to the 2 factorial plus x cubed to the 3 factorial plus so on, x to the n factorial. Okay, so if I use this to model the AC component, or the small signal component, I could replace that exponential term with a Taylor series expansion of that, because we know that exponential term is challenging to solve for in a circuit, and we've come up with methods to solve for or diodes because of the challenging nature of solving for the operating point. Okay, so I could replace that exponential with terms, a series of terms from this Taylor series expansion as such. Okay, and we could keep drawing those out to get more and more precise. But you'll recall that our definition of a small signal back some while ago was a signal or a diode voltage that is, let's say, less than or equal to NVT. And we know for a silicon diode that N might be as large as, our ideality factor might be as large as 2. So we're talking about values here in the range of 50 millivolts, kind of on the larger end for silicon diode. Okay, so based on that magnitude here, so then if we consider the magnitude of these terms, so if VD over NVT were if VD and NVT were equal, as suggested here, kind of for the maximum case to define a small signal, well then the square of that, so if VD is we're talking about VD being less than NVT, or as much as being equal to that, squared times the half, this is generally going to be much less than VD over NVT. Okay, so this term might be as high as 1. This term on the right might be as high as a half, but often is going to be much smaller than that as our VD term gets smaller. So generally this term here is going to be much smaller than the term on the right. So all of that to say that all of these terms over here become essentially negligible compared to the initial terms. So using that idea, so similarly we can say that for the higher order terms are just going to keep getting smaller and smaller than the first couple of terms of our Taylor series expansion. So these are just going to keep getting smaller and smaller, and therefore we can make the same argument that they're negligible. So we can make an approximation of, for small signals, we can say that the small signal component is approximately equal to just 1 plus VD over NVT. I guess we can just use these braces. Okay, so if I just if I multiply this out here, we get ID plus ID VD over NVT. Okay, so this component of the current is the large signal component. This component of the signal is the small signal component, or maybe what we want to call lowercase I, lowercase d. And I guess I should continue to be careful here that this is approximately equal, but for generally the magnitude of signals we're talking about for being small signals, this is a pretty good approximation. Okay, focusing on the small signal component of the current here a little bit further. Okay, so just focusing on this part. I'm just going to draw the VD term out of there, the small signal voltage, and this term is what we're going to refer to as our small signal transconductance. Right? If you look at that equation, you'll note that we're basically in the form of Ohm's law here, where we've got current is equal to a conductance times a voltage, right? V equals IR, but if we rearrange, this is basically 1 over R here, or I is equal to V over R, so this is representing a conductance, and we're going to call it a small signal conductance, which we'll call G subscript M. Okay, and you might think, well, this value, because of the current term in here, this value is going to be changing, but we're assuming that our large signal component, that bias component, is fixed. So our diode is operating at a fixed forward bias, or due to the large signal, which is unchanging, but it's just the fluctuations in our small signal that we're now interested in. Okay, so if I now rewrite my equation for my small signal diode current, it becomes a nice, clean, linear equation. Okay, and again, this is much easier to deal with than what we were faced with earlier, our exponential form of our equation. Okay, so and we can if we go back and look at our IV characteristic here again for our diode, we can kind of appreciate that this transconductance term is resulting from the fact that we're biased at a specific bias point, and the fluctuations are only small around that point. So when we consider that, we only need to look at the operation set over a small region, and over that region we can assume that its operation is linear over small fluctuations. Okay, so linear small signal conductance is what is represented by the slope of that curve. Slope of the tangent here. Okay, and that's when we talk about small fluctuations around this bias that's a result of this the DC signal or the bias signal that's applied. And again, we can bring in a little bit nicer form of this figure from Cedric Smith, which shows our bias point. We have our tangent line shown in blue, and rather than calling it a transconductance, they're looking at the small signal resistance, right? And of course, that's easy enough to appreciate, that we can, rather than refer to it as a conductance, we can refer to it as a small signal resistance, which is just 1 over the conductance. And remembering that the origin of that conductance was ID over NVT, our bias current divided by our ideality factor times our thermal voltage. So now, looking at it from the resistance perspective, our small signal resistance is equal to our ideality factor times our thermal voltage divided by our DC bias current. Okay, let's so there's, what it comes down to here is when you have a combined signal applied to our diode, we can separate these solutions out, do our solve for our DC conditions, our bias conditions, that large signal solution, and then using that information, we see that we feed the large signal component into our small signal model to move forward with our small signal solution. So let's talk about that a little bit further. So this allows us to separate our solutions into our large signal solution. And the large signal solution, we've looked at a few methods of solving for the large signal, right? Maybe we call this large signal methods, and I should say, maybe I say separate solutions and solve for large signal first. Okay, so we can, using the exponential model, again I'm using a slightly simplified exponential model, and we could use the iterative method to solve for this. We could also use, okay, so this is one approach. The other approach would be our piecewise linear model. In which case we replace our diode with a model that has some fixed forward voltage drop, we call VDO, has some large signal resistance and an ideal diode, and then our diode current we can solve for to be approximately equal to the in this example we the voltage applied to the diode minus the forward voltage drop divided by the large signal resistance. Okay, so and of course we could get even to even simpler models where we go with a constant voltage drop model, and we're getting to a not very accurate solution then, and really we can't very precisely predict our bias current at that point. So I would probably not go simpler than a piecewise linear model if we're trying to get some precision. From here, now we can revert to our small signal solution, where we solve for the small signal diode current using the transconductance term. And that transconductance term is relying on us having already solved the large signal diode current through one of these methods up above. Okay, so we're going to take either this or this to feed into the small signal solution. Okay, so the total solution is going to be the sum of both parts. Okay, as we stated here at the beginning, right? The total solution is the sum of the input signal here is the sum of the AC and DC component. So of course the resulting current is going to be the sum of the bias current and the AC component, or the small signal component. Okay, and again, just a note here, I think I've made it clear here above, but note that in order to determine the small signal component, we first need to find the large signal component. Okay, so just revisiting our models, because I know there's been some confusion about this. So let's revisit our large and small signal models here again and compare them. Okay, so our large signal model, if we use a piecewise linear model, for example, the large signal model is going to look like this. And again, be careful of your naming of the resistance here with a capital subscript D or an uppercase subscript D. Okay, and the ideal diode here itself is essentially just treat it like a short circuit when forward biased. Okay, so how this relates to the IV curve here is often I get these backwards here, sorry. Often what we are doing for our large signal model is we're just trying to find kind of a best fit, and often we're doing this maybe over the operating range of that large signal. So this is often going to be through a couple of points. Again, if our operating region is very tight to a specific point. Of course, that doesn't really describe large signal operation. So large signal operation, we're usually operating over some range. So we would come up with a kind of a best fit over this range. So maybe we find 2 points that represent our range of operating points. We draw a line through those points where it intersects the voltage axis. This defines that forward voltage drop that's in my model here. Okay, and of course we treat it like it's off with no current flowing up to that point. The slope of this line, whether it's tangent to a single point or through 2 points, the slope of this line that represents the large signal is 1 over our D capital or uppercase D. Okay, so let me try to make this line here a little straighter. Okay, this is supposed to be a straight line. Okay, so the large signal model, we care about where it intersects the voltage axis, because we are looking at the large signal. When does it come on, and what approximate resistance does the behavior most closely represent over the range of operating voltages that we are likely to encounter. Okay, so this is the large signal model, whereas the small signal model, we are only interested in the operation at a very specific point on the curve. Okay, that only the operation around that bias point or that operating point that we've called Q. Okay, so the characteristic, the exponential characteristic, of course, looks the same, the true characteristic, but we are only interested in how it behaves. And again, I haven't done a very good job of making this exponential here. That's slightly better, maybe. We're only interested in how this behaves from a small signal perspective at a specific operating point, which we'll often refer to as Q, the operating point. Okay, and that's due to the the applied large signal, or the bias, but we are only interested in operating at that region, so we draw a tangential line at that operating point, and we don't care where it crosses the voltage axis, because that's not relevant in our small signal model. Our applied small signals are never going to be large enough to cause us to our diode to stop conducting. Okay, so here the slope of this tangent that's drawn at the operating point is 1 over our small signal resistance. Okay, and if we look at the small signal model, we model it with an ideal diode, and again the diode here, we're assuming it's forward bias, so it's going to be always conducting. So really the whole model just comes down to being a series resistance, which is equal to the series resistance, which is equal to 1 over the transconductance, or is equal to ideally factor times the thermal voltage divided by my large signal forward current, the current that result from the applied large signal or my bias signal. Okay, and most importantly, we want to remember that the large signal resistance does not equal the small signal resistance. Okay, the large signal resistance comes from a slope that's representative of a best fit line over the typical operating range, large operating range that the large signal might encounter, whereas the small signal resistance comes from that slope that's very precisely at that operating point. Okay, we'll end this lecture off here, and I'll do one more lecture on diodes just to go through an example applying these concepts we've just looked at.